Welcome to the NASA in Silicon Valley podcast, episode 65. Joining me again today for the intro, we have Kimberly.
Hey.
Kimberly, tell us about our guest, or actually more like guests, plural, for the podcast today.
No problem. Basically, we have with us Bron Nelson and Dimitris Menemenlis, who join us from the NASA Advanced Supercomputing Facility here at Ames.
Yeah, and this is a slightly different episode from what we normally do through the magic of fiber optic connections. We had Bron here in the studio, but Dimitri was actually sitting over at JPL over in Pasadena.
Right. So Bron, a computer programmer here at the NASA Data Analysis and Visualization Group, he specializes in most of the coding that happens with our supercomputers. Whereas Dimitris, he's a research scientist at JPL, where he actually studies and uses the supercomputing capabilities to analyze global ocean circulation and its interaction with sea ice and all the cool oceanography that happens to be displayed on the Hyperwall here at Ames.
Yeah, this is a really cool thing about over at NASA. You always think of space, but when it comes to supercomputing, it's like everybody uses the supercomputers. It's like no matter what they're studying.
Right. And it's great because the visualizations are very helpful in investigating the data that they come with, that comes apart from actually using the supercomputers.
Yeah, and I got a kick out of this one because typically, being NASA in Silicon Valley, we talk about ourselves, but this was a situation where we have a different NASA center who's using the information, and this is typically how this works. You have other centers, other groups, all working together. But before we go too much into the podcast, into the episode, a little bit of housekeeping. We would love for your comments and suggestions. You can leave us a review on iTunes, Google Play Music, wherever you find the podcast. If you want to participate or just send us your thoughts, reviews, ideas, we are using the hashtag NASA Silicon Valley. We have a phone number, so that's 650-604-1400. Give us a call. We'd love to hear your thoughts, and we'll see how we can integrate that into an episode. But for today,
here's Bron and Dimitri.
Welcome, Dimitri. Welcome, Bron.
Hello.
So for folks listening, this is a little bit different because I'm sitting here talking with Bron in our studio, and we have Dimitri on the line, or through the magic of the interwebs from JPL, coming and chatting with us. So we haven't done this way before, so this should be a fun time. Okay. But so Dimitri and Bron, we always like to start the podcast with the same question, and it's, how did you join NASA? And for Bron, I would say like how did you end up in Silicon Valley? But in this case, since this is more NASA California, I'd say what brought you to the Golden State? So Bron, go ahead, man.
I actually grew up in Livermore, just
local,
30, 40 miles east of here. I was actually born in Kansas, but family moved out here when I was like 2, so I'm almost a native. But I was working for a variety of companies. I'm a computer person, and I worked for a number of different companies. I was working for a firm named Silicon Graphics and was assigned here on site at NASA Ames to help because they had bought a number of our computers. And then after the company...
And they pulled you in.
After Silicon Graphics went bankrupt again and cut my salary again, even I could see the handwriting on the wall at that point, and so I jumped ship, as it were, and went native, as they say in the biz, and started working for the customer that I was previously supporting. So that's how I ended up here at Ames.
Nice. So you're always into computers, not necessarily. I mean, NASA people are always thinking rockets and space probes and stuff. So, but you're always into the computers, and so that's how you came into this.
That's right. I mean, as I like to tell my kids, I'm not a rocket scientist, but I work with rocket scientists.
Exactly.
So, I know almost nothing about the physics involved, Dimitri here works on the ocean modeling. I don't know anything about that, but I know a lot about computers, and so I'm often a member of a team of people and I help deal with the computer problems that come up.
It is teamwork that makes the dream work.
Right.
So, Dimitri, talk about...
What a horrible thing.
I know. Yes. I got that from your neck of the woods, Dimitri. I think I heard it somewhere. I was walking around in L.A. I don't know if I was visiting Disney or DreamWorks or something.
What did you hear? What did you hear?
Well, somebody said teamwork makes the dream work.
Yes. Well, okay, my story, what I find really amazing, and I don't know if it happens to everyone, but as you grow up, the dreams that you dreamed as a kid that get realized are the ones that you really remember. So I'm sure I had tons of dreams when I was a kid, but there were 3 of them that I remember and that have been realized, and that's pretty amazing. When I was 6, it was 1969, and we gathered around the neighborhood TV. I grew up in Greece, so TVs back then were not very, did not exist. Not every house had one. My grandparents happened to have one, so a lot of people gathered and we watched the first astronaut land on the moon, and that was like super big impression on me. And of course, a lot of kids who watched that wanted to be astronauts. I'm glad I didn't become one because what I'm doing now I think is even cooler. But
Nice.
2 more things that I really, it was a dream, was MIT and Caltech. Those 2 institutions were just, so NASA, MIT, Caltech. And somehow, I don't know, randomly or accidentally or because these are the dreams that got realized that I remember, I ended up going from MIT to Caltech NASA. So I was doing oceanography as a postdoc at MIT, and there was this opportunity to come to JPL and work with this satellite that had been launched a few years earlier called Topex Poseidon that observed sea surface height from space.
Okay.
And sea surface height is like a dynamical boundary condition for the ocean. It tells you, it's like knowing low pressures and high pressures in the atmosphere, and then you can tell the winds that they're going to go around the low pressure and the high pressure. Same thing for sea surface height. If you know sea surface height, you can tell what the surface currents are. And the really cool thing that we do is from space, you can only see part of the ocean circulation. You can't observe everything.
Yeah.
You can see surface variables, depth integrated variables, and of course there's a sampling issue. Mm-hmm. So in order to make a complete story, you need to have numerical circulation models. Those are the really fun models that Bron and others at NASA Ames help us to run on the NASA supercomputer.
I was going to say that's probably like the perfect transition almost, because I'm sure anybody listening, they're like, Bron and Dimitri, like, you have one person working on a computer, one person looking at the Earth from space. How does that match together?
Bron, do you want to have a go at it first?
Go at it, sure.
Yeah.
So,
what brought you guys together?
Well, NASA brought us together. I mean,
Nice.
Dimitri was working with the people at MIT on this thing called the MIT GCM, the MIT Global Circulation Model.
Okay.
And it does modeling of the weather, if you will, the weather of the ocean as opposed to of the air. But it calculates a great number of things about
It's like temperatures and currents and
temperatures
stuff?
and speeds and more of the things than you could possibly imagine, quite frankly.
Okay.
Dimitri would be a much better source of exactly what it does. But as he mentioned, you have the sampling problem. You don't have sensors everywhere on the Earth gathering
Exactly.
data every minute. Mm-hmm. And so you have to essentially interpolate between observations. You know it was this temperature, on June 21st. You know it was this temperature on June 22nd. What was it like in between? And you don't want to just draw a straight line. That's hardly
that's hardly what you see in real life.
That's certainly not, and certainly not over the course of a full year. Right? You can't just draw a straight line between July and July and say that was the temperature that it was.
Yeah, exactly.
So that's of course a drastic oversimplification. But the MIT GCM essentially applies all the known laws of physics, the climatology, of oceanography, of whatever you want to call it, whatever ology you happen to like, to try to decide how you got from this point that you know about because you measured it to this other point that you know about because you measured it, and how did it, what was it like in between? And so you can get a good model of the way the ocean works and what's going on at a very fine resolution, at least potentially a very fine resolution. But in order to do that, you have this very complicated computer program that I did not write. Let me make it clear. Some other people wrote that. but then you need to run it on a very large group of computers.
I was going to say, I just can't put it on my PC at home.
No. So we ran this model on typically
70,000.
Yeah, we run it typically on 30,000, but the particular thing that we worked with Dimitri was 70,000 processors simultaneously. And we were trying to figure out both just how to get it to do that and how to get it to actually run faster as a result of doing that. And the part that I was particularly involved in was writing out the results. So you calculate all these numbers, but then you want to save them so that later on you can analyze them, or in our case in particular, we make movies out of them so you can see
like animations and stuff.
Yes, and very detailed ones. So we have a piece of equipment called the Hyperwall, which is essentially a big array of TV screens, and a single frame, a single moment in time is about 250 million pixels of imaging. And we have salt concentrations and temperatures and velocities and an enormous amount of data that the model, MIT GCM, is producing. And just storing it all and saving it all is a much bigger task than you might think offhand. And so we needed to not only produce these numbers at some relatively fast rate, but then also to store all those numbers at that same rate, not slow down the calculation. And this was a whole team of people. I mean, I'm sitting here in this chair, but there's, of course, a whole bunch of people that were involved both in writing the code and getting it to work, and then all the support people who made the computers themselves stay up for, and so on and so on and so on. But
and so I was going to say then. So Dimitri, is this just a matter of like you give Bron and you give the team like some raw data, some stuff that you do know, and then he works on that model?
So I'll answer that question, but first I want to go back to something that Bron said earlier, and that I think is a fantastic segue into explaining a little bit better what we do. So a line, Bron said that our model is more complicated than a line, and it is. But a line is a model. It's a model with two parameters. And let's say you have observations of that line, right? And they're all over the place. They have some noise. And then you try to adjust these two parameters, the place where it crosses the zero axis and its slope. And you try to adjust these two parameters in order to fit these points as well as you can, because the observations have errors, right?
Yeah.
In a way, and what a very efficient way of doing it, a very good way of doing it is called least squares. You try to find the line that minimizes the distance between the observations and the line in a least squares sense.
Okay.
That is exactly what we do with satellite observations and with our model. Now, it's a hugely more complicated problem because, as Bron said, the model is the equations of the model are nonlinear as opposed to a line is linear. There's a lot more observations, but the degrees of freedom of the model are hugely greater than the number of observations. So it's a so-called underdetermined problem. So we're trying to fit a description of the large-scale ocean circulation that passes to within some distance of the observations from space and also in situ. There are instruments in the water, floats that profile the temperature and salinity. So that's so I like the fact that Bron mentioned a line, and I was waiting to to pick up on that. Your second question, it was in terms of how we operate.
Yeah.
And we have this numerical model, which is called the Massachusetts Institute of Technology. It's actually a general circulation model, so MIT GCM. No, that's all right. Global is good because we do a lot of global things.
I was pretty close.
You were pretty close. And, we can actually run that thing on almost any platform. We can run it on our laptop. We can run it on workstations. However, to do really interesting problems where you the way that you run this model is you break up the ocean into little boxes of water,
Okay.
right? And the more of these little boxes of water you have, the more realistic your model is. You're capturing more and more of the physics of the ocean. And at some point, you can't just do it on your laptop. And that's when you go to people like Bron and many, many, many others at NASA Ames, the magicians, we call them,
Nice.
who show us how to do it, how to scale up that problem. That's the first thing that they help us with, which is just on its own is unbelievable. But the second thing that happens is once you've run that thing, you have no idea what's in it because there's so many numbers.
Yeah.
And there we also need help in figuring out how to look at those numbers. So the second thing that those magicians at NASA Ames do is help us to animate, cut, look at the physics, look at processes. One of the things I have to admit, that they do is find all the problems, all the bugs, all the things that are wrong with the model. They just, when they look at it, hey, what's this? Hey, what's this? And things that we had no clue. So it's really fun to work with them.
It was a very good point. When you visualize something, when you make a movie out of the data, and then your eyes look at it, your eyes are really good at picking out things that are bad. Whereas if you were looking at pages and pages of numbers, it would be almost impossible to tell that something was amiss, or that something was good for that matter. So, I work with the people that do the visualizations, although I personally don't do the visualizations. But I work very closely with those people.
And I like to grab those visualizations, turn them into a GIF, and put them online.
Yes. Well, we'll be happy to supply you with unending images, I'm sure.
So I'd imagine sometimes does it go kind of both ways? I think of over at Ames, we had like the aeronautics model where they have these theories of like how, and the models in the supercomputer of how airflow works, but then sometimes you put a plane in a wind tunnel to test it, kind of check the answers in the back of the book. Is there a similar thing going on with you guys where, yes, you're using the model to find things that for you, Dimitri, that you didn't know before, but also I'm guessing that there's probably some real data from the sensors in the ocean that then can help modify and tweak that model as well?
Yeah, absolutely. What I like to say when people come to me and they say, oh, you're a modeler. I said no, and they say, oh, he's an observationalist. I say, you can't use a model without observations, and you cannot use observations without a model. And basically, the way science works at kind of a very basic level is you look at data, you look at observations with your senses and augmented senses, you feel things around you, and then you try to explain them. And the way you explain them is you make models. And the models can be very simple. They can be a line, or they can be something conceptual or something back of the envelope, or they can be very complicated. They're nevertheless models. So with the models, what you want to be able to do is you want to be able to reproduce the observations that you see. So that's the very first thing. I mean, you adjust, you change, you tweak your model, you change the equations, you change the boundary conditions until you can reproduce the observations to the degree that you believe the observations.
As Dimitri said, the observations themselves may have errors too, so you got to be a little bit careful.
Okay.
You don't want to necessarily reproduce them exactly.
Exactly. And then once you have that, now you can make predictions. You can say, well, given this, I expect such and such events to happen, or such and such processes, and then you can then go and make focus observations to see if it's happening, or you can go and collect, gather, observations that you had thrown away and hadn't used, and use them to see if they support or if they disqualify, invalidate your hypotheses. So that's one way that models are used. The other way, of course, is to try to, better understand the physics just from a scientific curiosity perspective.
Giving another shout out to another NASA center on the other side of the country over at NASA Goddard Space Flight Center. When I remember I visited there, and they also had a hyper wall and they had some visualization set up. And I'm thinking this is along the same lines where it was like they had the globe, they had Earth, and then they would dive down in their visualization and it would get into the ocean and had all these arrows and different things. And it was just showing the different currents and the different flows. It's the same thing.
Very similar sort of thing. It's exactly so.
And so,
actually, some of the very nice Goddard visualizations are based on simulations that we did at NASA Ames. I don't know if
I'd imagine that they're all shared back and forth, and that all these teams.
So and one of the things we would really like to do, they have a very good atmospheric model at Goddard, and obviously, I believe we have a very good oceanic model.
With their powers combined.
It would be absolutely amazing to put the two together, because some of the most important things, actually, the things that make, why are we looking for oceans on other planets, on other moons? Because the thing that makes, one of the key things that makes life possible is, the presence of liquid, of ocean to start with. But in our case, since we don't live in the ocean, the interaction of the ocean with the atmosphere. And the ocean allows climate to be moderate, meaning that it doesn't get super hot and super cold. If you go to the desert, you'll realize at night it can freeze, even though in the daytime you can bake an egg, right?
Yeah.
So it's the oceans kind of store heat when it's very hot, release it when it's cold. So they have a moderating impact on climate. At the same time, they do the same thing for chemical quantities like carbon dioxide. So most of the carbon dioxide that we might burn through fossil fuels and put in the atmosphere eventually will be absorbed by the ocean. So the ocean is helping the atmosphere from, really exploding in greenhouse gases, for example. And there's many other examples. And therefore, what you really want to understand very well is the exchange of properties between the atmosphere and the ocean. And therefore, if we were able to put those two models together at very high resolution, to make them realistic, you would gain a better understanding of how things are transferred from one fluid, the atmosphere, to the other, the ocean.
So my mind immediately goes into the practical application, or if I was talking to my family in Ohio, explaining this is so cool. I mean, my brain first goes to weather patterns, like hurricanes, understanding the ocean flow, understanding the atmospheric flow, and computing this craziness and to understand it. Is there realistic applications in that way?
Well, it's not quite the same thing as predicting where a hurricane is going to make landfall. Yeah. This is much more retrospective about you take already existing data and try to munge it and try to understand. But the application really is to gain deeper understanding of how these processes work. Hopefully you'll be able to use that to make predictions, but at the very least to be able to understand how and why things are occurring the way they are. So a lot of the data that we worked on was actually gathered several years ago. It's not, not like last month, but we're trying to use that to gain an increased understanding of the physics of the model, to refine the model, to make a straight line is not so good, maybe a curve isn't so good, maybe it's got to be really squiggly. Whatever that model might be, how things behave, you want to refine the understanding of that. So it's somewhat more theoretical than is it going to be raining tomorrow? That's not really the kind of questions that we're trying to answer. But it is sort of more fundamental science about how and why do these things work.
So Bron is absolutely correct that our specific investigations are more theoretical, but they are nevertheless important for weather patterns eventually, in the sense that if you want to predict hurricanes and where they'll make landfall and whether they'll grow or they won't grow, you need to have a good understanding of air-sea interaction and of mixed layer depth, for example, the amount of warm water that's stored near the surface of the ocean. And one way that I think of our work is a numerical model is a reservoir of knowledge. So you basically, as you learn more and more about processes, you adjust things, change things in the model to make it a better representation of reality. Then these models in turn can be taken by more operational agencies like NOAA, for example, and used for very practical applications. I would say that the most practical applications that we work on are not at the edge. It's so what the kind of model we're developing now will be used for practical applications maybe in 10 to 15 years. Right now, really, we're pushing the envelope. We're exploring what's possible. We're learning. 10 years ago or even 25 years ago, we were also pushing the envelope, but with models that now are really easy to run because of the increased computational power. So the models that we're actually using in quasi-operational capacity as part of one of the projects that I'm involved with are models that were cutting edge 15 or 20 years ago. So there is this progression where you improve the model and then you start using it for more practical applications.
Yeah, there's certainly plenty of analogies one could paint. If you say the wind tunnels, if you're doing, shall we say, fundamental research in aerodynamics, you want to know about turbulence, you want to know about streamlining. That's not the same thing as designing a car that gets good gas mileage, but eventually you hope that because you did all these experiments to gain increased understanding of the fundamental principles behind it, eventually that knowledge will get incorporated into, as you say, more practical everyday applications. So no, you're not going to see the results of the stuff that we work on, on your local Weather Channel next week, but it is still a very important investigation.
So talk a little bit about what you guys see, in the near or in the future, looking like 5 years, 10 years from now. What are you guys going to be sitting around working on? What numbers are you going to be crunching? Or where would you like to see things go, I guess?
I'd like to be retired myself, but
we're not going to let you retire, Bron. You're too good.
As soon as my kids graduate from college, then I'll think about retiring. But until my kids graduate and my mortgage is paid, I think I'm kind of stuck.
Come on, you like working with us.
Yes, you're right. I do. It gets me out of bed in the morning.
Yes.
Or sometimes in the afternoon. Right now, I really see the thing that Dimitri mentioned, which is trying to couple this to other pieces. This is an ocean model, and it's very large. We're doing whole Earth simulations, right? Not just
This isn't small scale.
Not small scale. We're doing
big. We're doing the big things.
The big thing. And as Dimitri said, you do this by essentially cutting the ocean up into little boxes and studying the boxes. And right now the boxes are about 1 kilometer on a side, which when you're talking about the whole Earth, that's a lot of boxes.
I was going to say.
And we just recently did a simulation where the boxes were 100 meters, 250 meters on a side.
And 25?
Oh, that's right, 25. But that one didn't work for some reason, right?
No, it did. It did.
Well, but in any event, but it's not over the whole Earth, just over a small portion.
Okay.
So increasing the resolution, more processors, better resolving of all of these factors. That's certainly a place, but that's sort of a quantitative difference rather than a qualitative one. It's the coupling of it with atmospheric models or with ice and so forth that Dimitri's heavy into ice. So
ice is nice.
But that I think is the direction that you want to thing that will be new and interesting, if you will. So Dimitri, as long as I have you here on the phone,
yes.
Could you explain to me what the difference between coupling with a Goddard model and, say, the MM5 or 6 or whatever they're up to now at NOAA is? I mean, because that's a coupling with land.
This is
water,
a good way to
earth,
get him to
everything.
answer that email you sent.
Yeah, it is.
No, there's no difference. There's no difference, really. I want to beg to differ on at least on one point. As you increase resolution, things change. If you want to think of the ocean not in space-time, but in frequency wave number, and those are big words. Frequency has to do with wavelengths in time, and wave number is wavelengths in space. Mm-hmm. You can draw bubbles, if you like, bubbles of different processes that occupy different lengths and time scales. With 1 kilometer, what we're capturing very well is what's called geostrophic eddies. So they're eddies, they're motions that feel the rotation of the Earth. So in the atmosphere, these would be the storm systems, if you like, which have 1,000-kilometer scale. In the ocean, the scale, because the fluid has a different density, and also the stratification, the fluid, and also the stratification of the density from the surface to the bottom of the ocean, the scales are much smaller. They range from like 10 to 100 kilometers, the scales that feel the rotation of the Earth, that is. And with 1 kilometer grid, we're capturing those incredibly well, which is very nice, because before that, we had to create Band-Aids. Because we could not really resolve these in our models, we had these Band-Aids. They're called parametrizations that would try to approximate how these things would work if there's a lot of them. But these so-called parametrizations, they just don't do justice to the complexity of the circulation of the ocean. So now, with 1 kilometer, we're capturing these features, but then there's other bubbles that we're not capturing. There is bubbles, there's something called submesoscale processes. There's something called internal waves. We're starting to touch on those. We're starting to see them in the same way that 10 years ago we could start to see eddies in our simulations, but we were not fully resolving them. So we were kind of in this no man's land where should we be representing them or parametrizing them, or should we trust these crude representations in the model are useful? So now there's a bunch of processes that we're not resolving and that we are still representing in a crude way in the model. So as you increase resolution, you don't just, it's not just more of the same. There's different processes that kick in. So that's kind of really fun and instructive.
Where are you going to go from here? I mean, I agree with you. I'm reminded of a maxim of computer science or whatever, that a factor 10 in quantity is a change in quality.
Exactly.
When something gets 10 times bigger, things are different, even if it's sort of in
no
some
judgment,
sense.
but different.
But well,
better, small, bigger, better.
I mean, when your computer
worse.
is suddenly 10 times faster than it used to be, it's not just that you can do the old things 10 times faster.
Yeah.
You can now suddenly do new things that you couldn't have done before.
Oh wow!
And
Exactly.
so, in the same way, I think Dimitri is saying it's not just that you can see the same old things better, but there are these new things that you didn't even know were there, or that you knew were there but couldn't see
couldn't look
before.
at.
But now suddenly your magnifying glass is 10 times more powerful than it used to be, and you can actually see these processes. So that's a very good point, and thanks to Dimitri for correcting my offhand comment.
Well, like I said earlier, a model makes predictions. So one of the things we're super interested in is we're going to make some predictions, and NASA is actually launching a very nice satellite in 2020 or 2021 that's called Surface Wave Ocean Topography. We're going to make some predictions, and that satellite is going to tell us whether our predictions are correct. And then that's and also allows to change the model in order to better represent what the observations see. In terms of quasi practical applications, a couple of things that I'm really interested in and I'm involved with is application of these simulations to study interaction of the ocean with ice. And when I say ice, I mean both sea ice, which is ice that forms when the air is very cold, which is formed from ocean water and floats and cracks, and it's actually really beautiful, both in real world and also in the simulations. But also and that sea ice is important because it's like, think of it as a piece of styrofoam on top of the ocean. So where that sea ice is, it inhibits exchange between the atmosphere and the ocean. When you remove it, you start exchanging things, and that's important to know for many processes that have to do, for example, with regulation of the weather patterns and of how warm or cold the atmosphere is. But also in terms of biology, as soon as you remove the sea ice, some biology that wasn't there can, start to grow. In terms of uptake of carbon, so sea ice is important for that. A second type of ice we're very interested in is land ice, and that is ice that is formed by accumulation from snow. If you have a region where the amount of snow that falls every year is a little bit more than the amount of snow that melts every year, you form what's called glaciers or ice sheets. And these ice sheets are covering, for example, Greenland and Antarctica, and they're on land. If these were to melt and to return to the ocean, or if they were, we assume that they're in some sort of steady state, and the amount of snow that falls on them every year is about the same as the amount of ice that melts at the edges. That's good. That means the sea level won't change. If they start melting a little faster, well, we care about that because it means sea level will rise, and we need to know about it so we can, take action in terms of protecting coastal environments from erosion and other things. So I think that, and also the interaction of the ocean currents with biology, ecology, and carbon cycle, those are some of the things that really interest me.
Everybody should stay tuned for more to come, especially in 2020, as the work gets further complicated, and Bron here is trying to kick his kids out of the house. So
they're just going to come back.
So for folks that are listening that want to get more information, we're on Twitter at NASA Ames. We use the hashtag NASA Silicon Valley. But until we change the podcast name to NASA California, then that's what we're using in the meantime. But thanks a lot, Bron, for coming on over. And Dimitri, this has been awesome. Thanks for calling in from beautiful Pasadena.
Thank you very much.
All right. Well, thanks a lot, guys.
Sure thing.